Hello, fellow UMCP students, specifically those of you who are in ENME462 right now and working on homework 3. If you don't fit into that category, you're fine to stick along for the ride if you want to, but I wanted to make this video for them to help them out with homework 3. So for those of you guys who are working on this guide now, and you have until next Wednesday, the 27th, you're probably going to be solving problems 1 through 2 using Cramer's rule because you were shown that way in class. And that's fine and dandy. It makes getting transfer functions pretty easy, I'd say. The only problem is that it requires determinants. Now, if you're doing a determinant of a 2 by 2 or 3 by 3 matrix, you can do that whole crisscross thing that you were shown in class, and it's not a really big deal. When you're doing determinants of 4 by 4 matrices or larger, you're not allowed to do that rule because that rule is really a shortcut to the actual definition of a determinant. If you haven't taken linear algebra yet, you probably don't know how to take a determinant of those kinds of matrices. My goal here isn't to teach you how to do a determinant by hand. You can Google that if you want to. I'm going to show you how to do a determinant in Matlab so that you can solve through these homework problems a bit more easily. And if you want to do the work by hand, you can check with Matlab to make sure that the work that you're doing is actually accurate and correct and everything. So I'm going to do that by showing you guys how to make symbolic matrices and how to take determinants of them. By now you should know how to make matrices in Matlab, like a simple 1, 2, 3, 4, a simple numerical matrix. You guys have probably learned how to make these kinds of matrices in Matlab by now. If not, then you can look it up online, I guess, but it really isn't that difficult. What's really cool about Matlab is that you can also make symbolic matrices. So if I declare a symbolic variable s, which I can do by typing that command there, then I can make a symbolic matrix. For instance, I can do this. Have s squared plus 3, negative 1 over s, 7, and negative 2 times s. Right? I can declare this matrix, and now we have a symbolic matrix, where a11 is s squared plus 3, a12 is negative 1 over s, a21 is 7, and a22 is negative 2s. What's also cool is that I can take a determinant of this matrix. There's a determinant command just called det, D-E-T, and I can say take the determinant of matrix A, and that'll give me this answer. So Matlab can take determinants for me as well. And that's how you can approach problem 2b specifically on the homework, because if you do problem 2b, you're going to end up with 4 equations and 4 unknowns, which means a nice lovely 4 by 4 matrix that you'll have to take a determinant of. Now, if you want something that's more physical as an example, I've made something for that purpose. Let's say we have this going on for us, right? So now you can kind of see what those would look like with an actual problem. Let's say we already have our circuits problem in matrix form, in our AX equals B form, where this is our matrix A, this is our vector with our variables, and this is our vector with our solutions, right? And we're asked to find the transfer function V out over Vn, given that I2 is equal to 1/2 of V out. Now, if you're wondering where this actually comes from, I just, for practice, made up my own circuit. So here's the circuit where that matrix and those equations came from. You can set up that equation by yourself for practice, but I don't want to take up time in this video doing that. I just want to show you how to solve this thing in Matlab. So let's go ahead and do that. Okay, so now I'll declare the symbolic variable s. I'll declare a matrix A. Alright, the first part is 4 plus 1 over s. The second is negative 1 over s. The next part is negative 4. Drop down. I have negative 1 over s plus s plus 2, negative s. and -4, -s, and 4 plus 4 times s. Close that matrix, declare it. Just want to make sure that all of this is correct. This is looking fine. Yep, looks good, and it's symmetric like it's supposed to be. So there's matrix A. Now matrix B includes the VI, the input voltage. So I'm going to declare another symbolic variable, VI, so that Matlab can handle that when it does determinants and such. So I've declared that as a symbolic variable, and now I have B equals VI 0, 0. So now I have B, I have A, and I'm going to declare one more matrix. Recall that for Cramer's rule, since we're solving for the I2, we'd have to replace the second column in matrix A with the solutions vector, right? So I'm going to declare a matrix C. I'm going to set that equal to A, and then I'm going to replace this column with this column. So I'll say C, column 2, equals B. So I just replaced the middle column here with the solutions vector. And now I can use Cramer's rule. And from Cramer's rule, we should know that I2 will be equal to the determinant of C divided by the determinant of A, in this case, where A is our matrix with all the coefficients, and C is the matrix where I2, the section for I2 is replaced with a solution vector, right? So I'm going to do that. Matlab is going to spit that out for me beautifully. However, I want V out. If I2 equals 1/2 of V out, then V out equals double I2. So I'll declare V out equals 2 times I2. But I want a transfer function with V out over Vn. So I'll declare one last variable, trans function equals V out divided by the symbolic variable Vn. And I end up with this. And this is my solution. This is V out over Vn. It might not look that appealing, so I can actually make this look prettier by using the pretty command on this guy. And there, that looks much better. So here's our transfer function in a much more, legible form. And our transfer function V out over Vn is equal to 8s squared plus 8s plus 8 all over 12s cubed plus 35s squared plus 20s plus 8. So there's our answer to our particular problem. Hopefully that helps you with how to tackle the problems on the homework, especially 2B. So yeah, have fun taking determinants, I guess.